Hi everyone. We are going to start a conversation about chapter 12, which is about equilibrium. The end of chapter 12, section 4, also has to deal with elasticity as well as like stress and strain on particular objects. But AP Physics C objectives say, hey, we don't need to know anything about elasticity, so our conversation is only going to focus on this equilibrium, and specifically, we're just going to focus on static equilibrium. So for our objectives for this particular chapter, we're going to talk about just what equilibrium means and then what particularly static equilibrium means in friction. What are the static equilibrium conditions? So I need a net external force that must be equal to 0, but I also need a net external torque that must be equal to 0 if something is going to be in static equilibrium. So these are the conditions that we'll talk about, and we'll do several problems. So solving static equilibrium problems. We're also going to kind of go back over center of gravity. We talked about center of mass. Center of mass and center of gravity are very, very similar ideas. But for some reason they decided to throw center of gravity back in this chapter, so we're going to talk about it again. Okay, so static and dynamic equilibrium. Ultimately, we know that equilibrium implies that an object is going to be at rest. So if an object is at rest, we call that static. If its center of mass, we say is moving with a constant velocity, we call it a dynamic equilibrium. So that's the difference between the two. So if we're at rest, then it's a static equilibrium, but if it's moving with a constant velocity, constant speed, then we have dynamic equilibrium. Don't care about this here. So ultimately, static equilibrium is our focus, and that's when we have linear and angular velocities that are equal to 0. So just my sub, Cm here, is just representing that it's the velocity for the center of mass, because we're representing the particle is moving all together like it would be as it's moving at its center of mass. So my velocity at center of mass is 0, and the angular velocity is also going to be 0. So there's several different examples I have listed here, and these can be both static, and we can have some that would represent dynamic equilibrium. So some of these conditions that need to be met for equilibrium to occur. First condition of equilibrium is just a statement of translational equilibrium. So now we're just talking about linear type of motion. I need the net external force on the object to be equal to 0. So ultimately this means the forces that are acting on this object should all be balancing one another. So I shouldn't have any type of acceleration here. So my F net is going to be equal to the sum of all of the external forces. So I may not just have one force that's acting on an object. I may have several forces. So I'm going to take the sum of all of those forces that are acting externally on this object. If I add those up and I set that equal to mass times the acceleration of the object, should give me 0. So this is just a restatement of Newton's second law at equilibrium. We've already seen this before. So this is just stating that the translational acceleration of the object center of mass must be 0. So if the object is modeled as a particle, because usually we model objects as particles, just makes it easier for us, then this is the only condition that must be satisfied. So I just need to think about all of the external forces just need to be equal to 0. The second condition for equilibrium is going to have to deal with rotational motion. So this is dealing with translational motion, but now if I think about rotational motion, I want to think about torque. So if I'm thinking about torque, I want the net external torque that's acting on an object to also be equal to 0. So rotational analog for Newton's second law would be torque is equal to I times alpha. So I meaning that moment of inertia times alpha meaning that angular acceleration. So that should be equal to 0. So ultimately this is just stating that the angular acceleration of the object should be 0 as long as I'm thinking that I'm in static equilibrium, and I know that there's a net external torque on the object is 0, that means that my angular acceleration of the object must be 0. And this must be true for any axis of rotation. Okay, so just in summary, net force has to equal 0, net torque must equal 0, and both of these conditions must be met, and typically we use both of these conditions to describe rigid objects in equilibrium, and that's what we're going to do. We're going to do several examples of those here in chapter 12. Guys, and we've already been doing this. You've been doing problems when net force is equal to 0, where I can say that the normal is equal to the weight force, and I know then that the normal must equal then the weight force. So we've been doing that net force equals 0 for a while. There should be no difference than if I'm talking about equilibrium and net torque, that my torques are going to end up having to balance somehow to make the net torque equal to 0. So ideas are here, we just are now going to bridge these two things together into one big problem. So a couple different things. Ultimately, if we talk about different planes for forces, I need the net force in the x direction to be equal to 0. I need the net force in the y direction to be equal to 0. And then oftentimes we like to restrict an application of forces only in the xy plane, because 2 dimensions is challenging enough. So usually when we talk about force, it's going to be in the xy plane, and usually when we talk about torque, it will be in the z axis. So based on the fact that forces are going to be in the xy plane and torque will typically be in the z direction, or we have the net force in the x direction must be equal to 0, the net force in the y direction must be equal to 0, and then the torque that's applied in the z direction is also then should be equal to 0. So it's just showing us that I can break this apart into components, and I should also get that the net forces or the net torque in all directions should be 0. Okay, so let's say, for example, that we have a seesaw, and that's consisting of, it's a uniform board of mass M and that subscript PL, so we'll just call it like plywood. And then that seesaw has a length, which we'll call L, and that's going to support a father and a daughter who are at rest. And let's say that the father has a mass that we will symbolize with capital M, and the daughter has a mass that we'll symbolize with lowercase m. So the support is under the center of gravity for this particular board, and we know that the father is a distance d away from the center. So if this is my pivot point, this is my center of gravity here, the father is a distance d away, and then it says the daughter is a distance 2 meters away from the center. So we actually know this distance from the center to the daughter is 2 meters. So we have 2 different problems that we want to solve for here. First one, let's find the magnitude of the upward force, which is just a normal force N, exerted by the support on the board. Okay, so find the magnitude of the upward force, just a normal force N, exerted by the support on the board. The second problem that we're going to do is we're going to find where the father should sit to balance the system so that it is at rest. So ultimately, they're at rest right now, but I want to show just using symbols where he needs to sit to make sure that he keeps that system at rest, at balance. So in A and B, really they've given us no numbers other than this 2 meters. So I have a lot of symbols, which means this is going to be a symbolic problem. So it's okay if we don't have numbers, it's a symbol one. So ultimately, if I'm looking at the different forces that we have here for the father and the daughter and the seesaw, so I have a center of gravity of the board. So that center of gravity I'm going to see with a vector here. The daughter has a particular weight force that's directed downward, so she has weight force that's directed here. The father has a particular weight force, his is directed down. You will note that it should make sense that the weight vector for the father is going to be larger than the daughter, because the father should probably weigh larger than the daughter. And the other force that I have acting is I have the support that's applying a normal force on this seesaw, on that board, on that uniform board, to also counteract then that center of gravity. So these are the forces that I have acting. And now, just drawing another picture, daughter's here, father's here, center of gravity for the board is here, and the normal force from the support is pushing up on the board. So those are all my forces. I've designated the length of the board here. I know that the daughter from the center is 2 meters, and I don't know where the father is sitting. So on this diagram, I just called it X, even though I think on the last slide we called it D. I'm sorry. Okay, so first let's do A. Find the magnitude of the upward force exerted by the support on the board. So I want to think about all of the forces that are acting in the Y direction, because ultimately the normal force is a force that's acting in the Y direction. So the net force in the Y direction is equal to N. It'd be positive because it's directed upward, minus mg, so there's the weight of the daughter, but I also have the weight of the actual uniform board itself, so minus the mass of the board times gravity, that's here. Then I also have directed downward the mass of the father, which is my minus mg here. And since they're at rest, this should be equal to 0, so then I could rearrange this equation for the normal to say that the normal is equal to, ultimately I could even go a step farther and let's take g out, where I would say n is equal to g times the sum of the masses together. So A is really easy in trying to find the normal force. B, so it's a little harder. B says, find where the father should sit to balance the system to be at rest. So if I need the father to sit in a particular place for the system to be at rest, I know that I've already dealt with my forces. I need to think about what's going to make the seesaw start to rotate in either direction. So I'm thinking about torque then, if I'm thinking about the net torque. If I think about it logically, the daughter can move a specific position up or down on the seesaw to possibly make this not be in equilibrium anymore. The father can also do the same thing. So because of that, I think about these two objects causing a torque on that uniform beam then. Because if this daughter moves, that could cause something to happen with torque, that could offset my equilibrium. If the father moves, then that could offset the equilibrium, causing this plywood to rotate about its axis or about its pivot point. So I'm going to say torque of the daughter and the torque of the father. So the father and the daughter could both apply some type of torque. I have the torque of the daughter and the torque of the father. We know that torque is just equal to R times F, our force times our lever arm. So our force here just being their weights. So I have mg times d here for the daughter, and d specifically here is 2 meters. So mg times d, which is just representing that 2 meters for the daughter. And then I have mgx representing the weight force. So mg is representing the force here, and then x representing then that lever arm for the father. But why is this one positive and why is this one negative? If the father moves in a certain position, ultimately he's heavier, meaning that that board is going to move down. If that board starts to pivot and rotate down, then the board is going to be moving in a clockwise direction. We said that if it moves in a clockwise direction, then it's going to be a negative. So that's why we have a negative capital MGX here for the father. The daughter is a positive because the father already is heavier. So let's say that we're not at rest. Let's say that the father is heavier and he could cause some type of rotation about that pivot point. The daughter still has a weight force, and the daughter is trying to counterbalance the weight force from the torque from the father in the clockwise direction to counterbalance giving a torque in the counterclockwise direction. So the daughter is trying to apply a force in the counterclockwise direction, which then would be a positive direction, so that makes it a positive mgd. So because all of this is at rest though, I know that this is equal to 0, so I can say that mgd equals mgx, and I know that d, this is for the daughter, this is for the father, the g's end up canceling out, so I just rearrange this for x. So I said, because I'm trying to find the distance here that the father needs to sit, so that way this is all at rest. So x is equal to the ratio of the masses, the ratio of the daughter's mass over the father's mass, times the particular distance that the daughter is sitting. Well, I know that distance. I know that that's 2. So I just plugged in, I have 2 meters here times the mass of the daughter over the mass of the father. And that should be less than 2 meters because this side would also have to be 2 meters, and he can't sit anywhere off of the seesaw, then it wouldn't be at rest anymore. So this would be my answer in finding where the father should sit to balance the system for it to be at rest. If we make sure and we check all of these things, the net force in the x direction, we don't even have forces that are applied in the x direction, so it's just 0. The net force in the y direction, all of them are balanced, so we know that that's also equal to 0. And then if we talk about the net torque, we said that the daughter and the father would be what would provide a torque about that particular pivot point, and ultimately we know that those would be balancing one another to set that equal to 0, so all of that should be 0 as well. So this is just there to show that we're checking and making sure that all of our forces and our torques are equal to 0. Okay, I just added this in, guys, to your slides, and like I said, I posted the slides on your blog. It doesn't matter which axis you choose for calculating a torque. Axis is arbitrary, and we've done a couple of these in different chapters of figuring out if I move my axis here, then what's going to happen? We're going to get the exact same answer. So ultimately, all I did was I worked this out for you to show what would happen if I think about the pivot point being at, we'll just say a place O, I call that the origin, or let's say that now we have a rotation axis at point P. So I worked it out at O, that's what we just did, but I moved the axis, my arbitrary coordinate system over here to P as my rotation axis, and ultimately we're going to get the same thing. So it doesn't matter where you place your axis, I'm just trying to show you should get the same thing as long as you're doing the math correctly. Okay, in class tomorrow, guys, we're going to start with center of gravity. So I think that pretty much gets us like halfway through our slides so far on chapter 12. So tomorrow in class, we're going to do a small a lab over angular momentum, just a little small lab. You'll have a small quiz over chapter 11, just a couple questions, probably like 2 questions, and one will be multiple choice. The other one I'll have you actually write out some work for me. And then we'll keep going with chapter 12 and do a couple book problems also from chapter 12 in class. And that's true for 5th bell. For 2nd bell, you'll be doing all of those things on Thursday. But 2nd bell, you should still check your blog tomorrow, just so that way you can make sure that you don't have any homework that you need to do for Wednesday in class. I know that kind of stinks about block scheduling, but that's just the bear that we have this week and next week. So I will see you guys tomorrow. I hope you have a wonderful night. Bye!